This is the solution to question 2D from work 3. So we have an equation that is written in the form m dx plus n dy. So that means that m is equal to x cubic plus y natural log of y minus 2xy. And n is x natural log of y minus x squared plus cosine y. Our first instinct should be to check if this is an exact equation. To do that, we take the partial derivative of m with respect to y, and we get y times 1 over y plus natural log of y minus 1 minus 2x, which becomes this is 1, this is negative 1, it cancels out, so natural log of y minus 2x. And the partial derivative of n with respect to x, that will be natural log of y minus 2x, which is exactly the same. So we have an exact differential equation. That tells me that there exists a function u such that the u is equal to 0, and the total differential, the complete differential, can be written as the partial of u with x dx plus the partial of u with y dy. Comparing this with the original equation, which is m dx plus n dy, we can say that the partial derivative of u with x is equal to m, and the partial derivative of u with y is equal to n x comma y. So it also follows that since m is equal to x cubic plus y log y minus 2xy, and using the fundamental theorem of calculus on this equation here, which I forgot to add numbers here, I'm sorry, this is going to be equation 1, this is going to be equation 2a, 2b, (3a), no, 3a is this one, which I'm about to write. U is equal to the integral from some x naught to x of m of t comma y dt plus some function of y. And that means that u is equal to the integral from x naught to x of x cubic plus y log y minus y minus 2xy. And one more time, that should be t. We're integrating with respect to t, that means y is to be taken as a constant. And well, that becomes t fourth over 4 plus ty log y minus ty minus t squared y. And we are to choose x naught such that this function here becomes 0 or a constant. And well, we see that we're multiplying by t everywhere. That means that x not equals to 0 should be a good candidate. And what this becomes x fourth over 4 plus xy times natural log of y minus y minus 1 minus x squared y. There you go. This will be equation 4. So I guess I could just call that one 3. Doing something similar for the integral with respect to y, we have that the partial derivative of u with y was equal to n, and n was equal to x log y minus x squared plus cosine y. By the fundamental theorem of calculus, we have that u is equal to the integral from y naught to y of n of s of x comma s. Plus some function psi of x. Integrating with respect to s, that means that x is a constant, so that becomes the integral of natural log of s, that is s natural log of s minus s minus x squared s plus sine s. All of this from y naught to y and we need to choose y naught in a way that they will make all this function 0 or a constant. We see that s, we have sine s, so if s was to be 0, that would vanish. Multiplying by s, we cannot make it 0. We could make it 1, and at least that term there will cancel. And well, we get u is equal to x minus, let me see, x times y, natural log of y, minus y, minus x squared y plus sine y, minus when s is equal to 1, this is 0, negative x minus x squared plus sine 1, and of course plus psi of x. Let's simplify that a little bit. So I have u is equal to x times y, natural log of y, minus y. Minus x squared y plus sine y plus x plus x squared, and this sine 1, we'll leave it there for now. and this is going to be equation number 5. Now we need to compare equation 4 and equation 5, so I'm going to bring it from the previous page. Wrong page. Equation 4. Put them side by side, make it easier. And let's see what we have. xy natural log of y minus xy, so that is this part right here, and I have minus x squared y, so that is this one right there. Let's write the common part first. So comparing 4 and 5, xy natural log of y minus xy minus x squared y. I don't have an x squared and x fourth over 4 here, so that would be our psi of x in my phi of y. Has a little problem. This one was not a function of y, so we need to go back and revise our choice of y naught. Basically I need to get rid of any instances where x is present, and to do that I would have to take probably s equal to 0. So yeah, I'm gonna copy this one and move it to the next page where we're gonna work on it. I don't see any other way in which this is going to be 0 simultaneously for all the terms in x. Let's take a look. I need it to be 0 here, and I need it to be 0 here. So s has to be 0. There is no way around that. See how that works. So that tells me that u is equal to x times y natural log of y minus xy minus x squared y plus sine y minus x that multiplies the limit as s approaches 0 of s natural log of s and this one is identically 0 and this one is identically 0, and so is this. So what is the limit as s approaches 0 here? Well, we know that the natural log is a continuous function, so we're going to calculate that. First using the properties of logs. Give me a second. Now we're going to use L'Hopital. Yes, L'Hopital would be easier. I will rewrite this in this way so that we have an undeterminate form, which would be negative infinity over plus minus infinity here, And using L'Hopital rule, this becomes 1 over s over negative 1 over s squared. Forgot the limit. Which I can then rearrange to get negative s. And well, that is simply 0, which is good. So this whole thing goes to 0. And it means that u is equal to xy, natural log of y minus xy minus x squared y plus sine y plus psi of x. Alright, so that is my new equation 5. One more time, I need to compare these with equation 4. So I have the xy natural log y term. Let's write it down. Use a different color. Comparing 4 and 5. Xy log y minus xy minus x squared y. All of those are shared terms plus a function of y exclusively. The only thing missing is the sine y. So that's good. And the only thing missing from here is x fourth over 4, which is a function of x. And this has to be a constant. And well, that is our solution. Now, to make sure that that is true, I need to differentiate this solution with respect to x. So taking the derivative with respect to x will give me I'm going to factor as much as I can. So I'm going to factor out here xy, natural log of y minus 1 minus x plus sine y plus x fourth. That was a 4, not an x. And this is of course equal to 0, the derivative of k with x. Taking the derivative, that will give me xy times 1 over y minus 1 plus ln y minus 1 minus x that multiplies the derivative of xy, which is y plus xy prime. This one should have been 1 over y prime plus cosine y prime plus x cubic equal to 0. Factoring out y prime, that's going to give me x for this one plus x times natural log of y minus 1 minus x and plus cosine y. And we're going to send the rest to the opposite side, to the right hand side of the equation, as negative x cubic here, and I have minus y that multiplies the natural log of y minus 1 minus x plus xy. I'm also going to rewrite this as dy over dx. We're going to multiply everything by dx, and I'm going to see what I can simplify. So for example, here I have x times -1, that's negative x, so that one cancels the other x here. This positive xy does not cancel that one. Let me take a look again. Maybe I'm missing a sign, or maybe it's just fine. Minus xy plus xy. It looks correct. We'll see. Multiplying everything by dx, I get x natural log of y minus x squared plus cosine y dy plus x cubic plus y natural log of y plus y minus 2xy dx equal to 0. Let's take a look at the original function. X log y minus x squared, x log y minus x squared plus cosine y, and x cubic plus y log y minus y minus 2xy. This is minus, yes, positive, that should have been minus. We'll multiply here and send back, yeah, and it's perfect. And that's all.